So, okay, I did my best. We are almost on time. It was incredible. Good. We're gonna continue the conference with first plenary lecture delivered by Professor Stefanie Hellweg. She's from Institute of Environmental Engineering in Swiss Federal Institute in Zurich. And Stefanie has gained an outstanding credential on the field of life cycle assessment and related issues. She's one of, really, from what I've seen on the citation in the literature search, one of the 3 top persons in the field with tremendous experience of linking the life cycle assessment approaches with waste and biomass issues. That's why I was very happy she could accept to join us and address this conference. I know she's very busy, and I appreciate she could come. And Stefanie, thank you. Please join us.
So, good morning, everybody, and thank you very much for the introduction. It's really a pleasure and an honor to be here. You know that waste engineering and waste management topics, they are getting more and more attention for a good reason. For example, in the European Union, maybe you've heard that recently the circular economy strategy has been approved. This does not only include waste prevention measures, but also the recycling rates, for example, will be very ambitiously increased. And that will definitely calls for technologies to actually help valorizing materials. So I think the topic of this conference is really up to date, and it's very, very relevant in that context. How does the current situation look like? This is just a picture of Europe and what waste treatment is, how waste treatment is structured here. So we have the different countries with very differing amounts of waste created. Interestingly, France, where we are at the moment, is representing quite well the average of Europe, so a good representative. We have not only differences in the amounts, but as you see from the colors, we also have quite different disposal pathways and recycling pathways in the different countries. So we have a lot of countries still counting very much here to the left-hand side, counting very much on landfilling. But we also have countries where we have quite a lot of recycling. For example, Germany, I think, is the front runner in recycling. So there's quite a big diversity. And as we can see here, there's still a lot to do, and that is not different in the world. In the world, you can see a similarly or even more diverse picture. Not only in the countries where we still have a lot of basic technologies, especially direct landfilling, but also in those countries which look very good on this graph. I will make the point later on that also there you have quite significant improvement potential still. Now, in order to get these improvements, we need technologies. This is the topic of the conference, not only technologies, as we heard, but also good products which result from that. And this is just a short overview of some of the sessions that you're going to see in the following days, and I think this is really up to date. Of course, this has a purpose. We would like to have this ideal, we dream of this ideal technology where we only have, let's say, some waste streams going in, and as a result, we get useful products out, high-value useful products out, and nothing else in form of energy and materials. Of course, this is never going to be perfect, but in order to get there as close as possible, we need tools to assess actually what we are developing. And I will talk today about environmental assessment tools which help to improve such technologies and products which help to quantify the environmental impacts and identify important waste streams and help to assess different technologies. If, for example, you can choose between various of them, or if you want to look at a technology and find hotspots in the life cycle of that technology in order to improve it overall. What are these tools? I will talk mainly about two of them, material flow analysis and life cycle assessment. There are more. For example, risk assessment is also quite important, but for the interest of time, I will restrict it to material flow analysis and life cycle assessment. Material flow analysis has been used very often in the field of waste management to support decisions. What we basically do, I'll quickly give a summary. We have a system boundary which, for example, can be a region, a country, for example, and we look at all the flows of substances or of materials into a range of different processes. And also, material flow analysis doesn't only look at the flows, but also at the stocks, for example, in the troposphere. As such, this tool can help, for example, to answer questions such as how much of a resource is available, either from primary resources or from secondary resources, by identifying here high-level flows, but also stocks, for example, in our economy that can be used in the future for recycling, for example. The other tool that I'm going to discuss, the applications of such, is life cycle assessment. As the name says, what we are doing is we look at the life cycle of products or of technologies, starting from resource extraction and then going over the production, use, and the disposal pathway. And we are looking at all the emissions and resource uses from these systems, looking at all these phases. And not only at the emissions and resource uses, but we also try to understand the environmental impacts that are associated to that. Typically, these are a range of environmental impacts. Today, I will mainly restrict to climate change effects to keep it manageable and overseeable. But most of the analysis that I'm showing, many more environmental impacts have been assessed in parallel. This is rather important because sometimes we have trade-offs between different environmental impacts. The type of questions that we can answer with life cycle assessment is, for example, if you have a range of different technologies for treating one waste or material stream, which one performs best from an environment point of view, so if you have to make choices, or on the other hand, if I have a certain technology, how can I improve it in order to minimize the overall environmental impacts and increase the benefits? So that was a bit about the theory and about presenting these tools. How are they applied? And I will give a range of different applications now, go in detail with some of them, and some I will just more or less mention so that it's a broad overview so that you get an impression of what can be done with these tools. The first example is actually an example from the Technical University of Vienna. This is a substance flow analysis of phosphorus. Please don't try to read the graph. It's too complicated. I would need probably the whole lecture in order to explain it. I will not do this. What I wanted to show is here what you see is this is Austria as a system boundary, and inside you see a lot of processes, and you see the flows of phosphorus between these processes, and you see some accumulations of stocks in certain of these, in some of these processes, for example, in waste management, because you have a lot of phosphorus, for example, that is in the sewage sludge, incinerated, and then ends up in landfill, just as one example of one of these pathways. What type of conclusions can you draw from such analysis? Well, these authors, for example, they concluded that Austria depends quite a lot on phosphorus. Phosphorus, as you know, cannot be substituted in food production. It is a resource that we need. We cannot find a substitute resource for it. And they need to still import quite a lot of that. But they also find some potentials, unexploited potentials of flows which they can use in the future to actually close more the cycles of phosphorus. And they particularly pointed to sewage sludge and meat and bone meal, which could, in theory, substitute 70% of the fertilizers. In theory, because of course you need the according technologies to make that phosphorus available, also plant available. So such analysis can help a bit to identify which flows can be used more and where certain problems lie. You can also do MFAs not only on single substances, on single elements, but you can also do it in entire material streams. So that is an example of an MFA for PET in Switzerland. where you can see, for example, that we have different types of recycling systems and treatment systems. So we have here 60,000 roughly tons of PET consumed every year in the whole country. 80% of that is collected separately for recycling. That sounds extremely good. Only 20% roughly is going into incineration. However, if we then go a bit further, we see that it's not as positive as it initially sounds. It's positive, but not as positive. We still have several residues, which we have to sort out later on, which then are also treated thermally. We also have other materials which can go into recycling, but it's not PET, it's PE. And we have different types of recycling. So we have closed-loop recycling, where PET is becoming, again, a PET bottle in the end. And we have downcycling, open-loop recycling, where we use PET, for example, in packaging materials or as fibers for textiles. And if we look, in the end, only at the closed-loop recycling, we see that about 15,000 tons are in the closed-loop recycling, which is of course, much less than the initial 80%, which is frequently communicated as a recycling rate. This doesn't mean that it's environmentally bad. This is just the material flow analysis. If, for example, the PET in the packaging material or in the textile fiber substitutes also primary PET produced from oil, this can be just as good as the bottles. But we are restricting flexibility, and this I try to show in the next graph. So, for example, here we have again our PET bottle. And we have, as an example, for comparison, a glass bottle. The glass bottle can be recycled into a glass jar, and the glass jar can, again, be recycled to a glass bottle. So that would still count as a closed-loop recycling system. So both, if you have the PET bottle recycling to a bottle again, and this glass cycle. However, if we have the PET bottle and we, for example, produce packaging material of it, this is open loop because the packaging material can never fulfill the demands again to become a bottle. So what we are actually doing is we are restricting a bit our degrees of freedom. We have an irreversible, let's say, process. We still have used the material, but we don't have the same degree of flexibility afterwards anymore. Now we can do this for PET, but we can also do it for other materials. And this is what I'm going to show here, again, for the example of Switzerland. On the left-hand side, we have the example that we just discussed. The black bars, they show the recycling rates which are communicated by the federal offices. So this is what you typically hear or read when you see the statistics, the official statistics. And these look extremely good. So you can see here for PET it's 80% or more than 80%, tin plate also. Aluminium is even over 90%, glass is almost 100%, paper also. So incredibly nice it looks, right? If we have a closer look with the type of analysis that I just presented, then we can understand these figures a bit better. So for PET we already did, and we have here in green we have the closed-loop recycling system, blue we have the open loop, and we can see that when we go really to the recycling rates, meaning what is ending up in secondary products in the end, we have a bit lower numbers because we have quite a few losses here. We have also here in yellow some other materials. So really recycling rates, we are here, and for closed loop, we are less than 30%, just as a background information. So these tools help to understand a bit better what recycling rate, for example, means. They give a kind of qualification to it. We can also see that we don't really know a lot about the system, because when you do these analyses, you find inconsistencies. For example, for the paper system, if some inconsistencies were found. As you can see, the rates had to be corrected. And that was because the mass balances simply didn't match. And then it was found out, okay, in the statistics, the amount of paper consumed was not estimated correctly because you have a lot of material entering the country by post, by the mail system, for example. This is also called the so-called Zalando effect because a lot of boxes come in and these are not accounted as consumption. And that is why probably the paper recycling rates were classified so high, almost 100%. And they could have been higher than 100% here because some of the inputs were not accounted for correctly. So we can see that also here in countries where, when we look at the statistic, it looks really, really good, we do have a certain margin of improvement. This was only about mass flows so far, but we can also attach more information to that. So here again we have energetic flows in this case. So this is just the energy content of the waste that is going into the incineration plants up here, and the energy content that is going into material recycling. It's about 50-50, again for the case of Switzerland, but you can do it for any country. Then the incinerators have a certain efficiency, and we end up with recovered energy of this amount here. And for the material recycling, we just have here the lower heating value of the different materials. Now, when we want to assess and understand a bit what these different treatment or recycling options bring, we have to look at the demands that they have, that the recycling or treatment process has in terms of, for example, in this case, energy demands. And then we have substitution of primary products or of primary energy. And that, of course, goes in favor of these technologies. And if we look at both and just look at the net cumulative energy demand over the life cycle of these flows, then we can see that actually we can save quite a lot. So for here, for the energy, for example, for the electricity and for the heat, if we would have to produce the same amount of electricity and heat with other processes, average for Switzerland, we would have to put in about 20 petajoules over the life cycle in order to get to the same, in the end energy. For the material side, this looks even a bit better because we can substitute primary materials which need a lot of energy during the life cycle to be produced. We are substituting even more. So the material recycling here, as you can see, pays off better than the energetic recovery in that case on average in Switzerland. This is just the average. Now what we can now do is we can pick certain of these flows, and I will do this now with the organic fraction, and we can try to compare different options of how to treat that. So this is here a mass flow analysis of this food supply chain. And we can see here from the agricultural production to the end consumption, we are losing a lot of materials. So in green, we see the flows which are intended for the consumption. And in colors, everything which is going down here, we can see all the losses during the whole chain. And overall, for 500 kilograms per person per year that we consume annually on average, about 300 kilograms of avoidable food waste arises throughout the chain, a very, very high number. Most of it in the households, and that is rather representative for other industrialized countries. In many southern regions, it's a bit different, then the households would not waste as much, but then often in the agricultural production stage, there are more wastes. Now, we can quantify the losses that we have here and attribute them to different processes in order to develop programs and measures which are targeted to where the waste actually occurs. And we can also compare different options for treating the food waste. And here's a range of options which are currently used. In order to assess those, what we can do is a life cycle assessment. Sorry, this was just adding a number. And here we can see the result of such a life cycle assessment only for the impact category of climate change. You can do other impact categories, of course, also. So in this case, for example, we also did it for land use, water use, impacts on biodiversity, etc. But just to keep it simple here is the graph for climate change. And this is now per person and year, the climate change impacts of food waste. In the upper graph, you see what effort we had to take to produce that food that was wasted. And here, some of the food categories, like vegetables, here show up because the mass of them that are wasted is extremely high. Others show up, for example, here the meat shows up not because the mass is high, it's expensive enough so that people don't waste it so much, but because the specific impact is very high. You need a lot of or you're emitting a lot of greenhouse gases in order to raise cows, for example, and to produce beef of it. This is what we are losing in terms of producing avoidable food losses. Now, once the food loss has occurred, we can, of course, treat it. And in most cases, because we have processes which, for example, produce usable products again, like fertilizers, for example, or energy, we often have then, let's say, a benefit. Yeah? So, for example, if we have here bread and pastries and we waste them, we very often can use them in the feeding of animals. And there we can, again, substitute other foodstuff. And this is why here we get a credit. Yeah, in the case of bread, it's actually quite significant. However, what we can also see, these are again the processes which are currently used, what we see here, the savings which we currently have in Switzerland. And what we can see is they are all very, very small, except for the bread. They are extremely small in comparison to what we are actually losing. So in this case, what we can actually deduce is that the first line priority should actually be the prevention, because anything you can do afterwards with the food waste is marginal in comparison to what we can achieve by just preventing more food waste. This is also clear from the next picture. So here we have just per kilogram now, per kilogram of food waste, different food categories in the different colors again. And again, looking at what we need for the process minus what we gain from it by substituting other materials. And here we can see very nicely, it doesn't depend. So first of all, again, the prevention is an order of magnitude. You can save an order of magnitude more by preventing food waste. But then when we look at the different processes, we see it depends on the food category, which actually performs best. But here the uncertainty bars, and that is more important, they actually show the uncertainty depending on what kind of product you can substitute. And that confirms a bit what Ange was saying in the initial lecture, that the quality of the products that you produce, they actually determine the environmental impact. The processes also, but first comes the quality of the products and what you can substitute. Because you can see here large overlaps between the different types of processes, but it really matters a lot what kind of product you are producing, what quality it has, and what kind of primary product you can substitute. And that seems to be more dominant as a driver. Good, this was a bit about some case studies. Now I will extend that to energy recovery from, in that case, municipal solid waste incineration. Here we have two things which I would like to highlight. First of all, we can recover energy, and then, especially in the latest years, we can also see a lot of processes coming up where you recover metals, materials from the solid incineration residues. And let's have a look at that and the potential of what you can save in terms of environmental impact from each of these strategies. So here we have an average municipal solid waste incinerator on the left-hand side. In red, we see the burden of incinerating the waste, again in terms of climate change impact, of the incinerator. And what we see in green and in blue are, again, credits given for the produced amount of electricity and the recovered amount of heat. Assuming that average European electricity mix would be substituted, so by producing electricity, recovering electricity, we would have to produce a bit less with the average European mix. And for the heat, fuel oil was assumed to be the reference system. So these actually need to be added up. Yeah, and we can see here there are quite a lot of savings in terms of climate change impact possible. The savings, they amount to about several 100 kilograms per ton of waste. And that is actually quite a lot. So that is good. We all know this. Here we also have two scenarios then. One for maximum electricity, very conservative. Actually, you can find better plants than that, but as you see here from the efficiencies, net efficiencies, but still, I mean, just being a bit realistic for the near term, and here maximum heat, and we can see, okay, if the substituted product is really heat from oil, which is the case in our country, then the savings would be largest by maximizing the heat recovery. That can change, though, in the future, because heat demand is going to decline in the future. Now, the second line is from the recovery, especially of metals from the solid incineration residues. We have quite a development there, and here we just find some concentrations of various metals in the ore, for example, here for copper, in comparison to that from different fractions of the slag that is from the bottom ash that you produce with municipal solid waste incineration. And you can see that in some of the fractions you have extremely high concentrations, which of course is a very good news, because that means if we can recover those, we can put them back into the cycle. And if we do the same analysis as before again, so again we have here in the positive range, we have here the impacts that we produce. For example, if we recover steel scrap from the bottom ash with a mechanical process, then we would have the red here would show the separation effort. So we have to put in electricity for the mechanical process. The yellow then shows, for example, the electric arc furnace in order to bring the steel scrap again into a state which is usable. And the green here would consider for the primary steel that you are substituting. And you don't only recover steel, but also copper, aluminium, other irons. So that is showing the status quo here. And you can see you can save about 30 kilograms of CO2 per ton of waste. So the potential is currently much smaller than for energy recovery in terms of climate change. It can be increased further if we increase the recovery rates by putting additional steps in the mechanical recycling. That was a question that the plant developer had. And yes, it does pay off. It's certainly a good thing. It's, however, not as relevant as the energy recovery. So these tools help you to a bit give you a prioritization tool. The same was done now, and I don't show the results, but for the filter ash, because there are also other processes to recover metals from the filter ash, wet chemical processes. And that was interesting because there you're much closer to a tipping point where it doesn't really pay off anymore to put more effort into the recovery to gain more metals out of it, because you put too much energy, you invest too much energy in order in comparison to the gain that you get by the recovered metal. So there was a tipping point. So, because this is a very long talk, I will give some intermediate conclusions. So first of all, just to summarize. So the material flow analysis, that can help to understand and identify potentials for recycling. As I showed with the example of the recycling rates, it can help you to understand a bit how these materials are treated and the quality of the recycling. The reversibility, for example, also. The LCA then helps to environmentally prioritize different recycling or treatment options. It also takes into account the products that you are producing, and by giving credit for high value-added products, it shows up in the results later on the quality of the products. What we can conclude is improvement potential exists in terms of the quantity and quality of recycling. That is not only true for countries which in the very initial graph showed up to not have a lot of recycling, but it's also true for countries which would classify themselves as waste frontrunners, like, for example, Switzerland. And then we had discussed some conclusions for the case studies. So, for example, for food losses, prevention should be a first-line priority. It shows this is really the first thing you should do, because it's an order of magnitude more that you can save by prevention than by any other treatment. For the municipal solid waste incineration study, it showed that in terms of climate change impacts, the energy recovery is really in the foreground, but there are other additional measures like the metal recovery, which are also very meaningful. If you look at other impacts than climate change, of course, the metal recovery can become more dominant. Okay, so let's put them into our waste bin. The second topic which I would like to discuss a bit more is the quality of recycling materials, because that is actually something which is very important. And it's nice that this morning Ange also said, okay, it's the quality of the product, and I will address that point also here now. So this is an example of the steel fraction, actually looking at primary data from an electric arc furnace, who was so kind to provide us with data about 18,000 steel batch processes. And we have the information here of what kind of scrap materials was inputted into each of these batches. And we had also, for example, information about the electricity consumption of each of these batches. And what we can see here is that the scrap that we get, for example, from the municipal solid waste incinerator, so that was just the process that I discussed before, demands a lot more electricity than many of the other scrap grades. This can be explained by various factors, among others, because there are still some minerals included in this scrap, and that leads to that higher electricity consumption. That is interesting because, I mean, you can, for example, clean this a bit better. You can put additional, maybe, mechanical processes. This is to be seen now in order to get the electricity consumption down in the recycling process, in the following recycling process. That would not be, let's say, incentivized too much by the recycling rates as they are currently defined or intended to be defined, for example, in the European Union, because they define it as recycling rate as the material that goes into the last step. However, you would like to clean this up, and then you have less material going inside, so the incentives would be in the wrong direction, unfortunately. But that is just a side remark. What I want to highlight is this additional electricity consumption in the recycling process as a function of the scrap quality, that is typically not considered. So it is very often that you assume that no matter what kind of scrap you have, the recycling process will consume the same amount of inputs. And that is not the case as seen here. That also then translates, again, into the greenhouse gas potential. So here we have in green the carbon footprint, and of course this is also a bit larger here for the bad scrap grades, for the low quality scrap grades, than for the high quality scrap grades right here. If we compare it to the carbon footprint of the primary steel production, here, and this is cut off, so noted, then we can still see any type of steel recycling makes sense here, so that is the good news, but within the secondary cycle we have some improvement potential. So, just to illustrate this in another way, so if we have a can, for example, it can go two ways at the moment. So it can go into the incinerator, and then you recover the steel from the bottom ash, and you put it then into the electric arc furnace. Or the other way would be to have a separate collection, again a pre-treatment, and then you put it into the electric arc furnace. And what we could show here is that depending on which way the material goes, in the incinerator we need about 560 kilowatt hours per ton of liquid steel. If we have the separately collected material, we only need 410 kilowatt hours per liquid steel. So we have 40% more electricity that we need in the subsequent recycling process. And that is quite a lot. This is not the only matter of secondary, let's say, material flow quality. If we look, for example, at the pollutants in these fractions, we also see that we have quite some differences here. So, for example, copper in the ferrous scrap recycling, it's quite detrimental because it's not good for the steel that you want to produce. It hardens the steel, and you want to avoid this because you cannot get rid anymore of it once it is in the cycle. And that is a certain problem because that means it accumulates if you don't sort out these fractions. So again, looking at the different scrap grades, we see here that the scrap from the municipal solid waste incinerator is polluted most. So it contributed most to the concentrations of copper. And also, of course, this is then transferred to the steel. That is something which also needs to be considered, and so far it has been very rarely looked at, that some of these metals actually accumulate once you increase recycling. And that is quite important because if you have elements like copper, this can actually eventually lead to the situation that sometime in the future you may have to dilute more your scraps in order to be able to recycle them at all. In another example, this has been shown by another group. In this case, this was the group of Daniel Müller in Norway. And they have done a dynamic material flow analysis for aluminium scrap. And they showed that very often many alloys are mixed. And the problem here is that recycled aluminium is of a lower quality and can only be used in certain applications. It mostly goes to automobile production, for some parts of automobile production. And they did this material flow analysis, and they showed that if we continue, as we do, in a business-as-usual scenario, within a decade, we will have a scrap surplus, because we do not have enough users of that material, because it's lower quality. And that, of course, is quite bad news. So they simulated this and said by 2050, we would have, according to their scenario, opportunity costs. So we would lose the possibility of recycling, and that is actually quite significant. They quantified it as being between 40 and 240 terawatt hours per year, or if you translate it again into the carbon footprint, 4 to 19 kilogram per capita and year. So just to show that it may be relevant, that here we have a problem coming up and that needs action. The quality of recycling streams is an important topic to look at. Another topic is that by including pollutants in the cycles, we may also have some health impacts because we may introduce some hazardous pollutants. So before I was talking about copper, and that was bad for the process and for the material. But for example, if those pollutants end up in plastics or in paper fractions, as investigated here by this group in Denmark, that can mean that eventually the recycled products may come in contact with humans and may lead to some exposure which you would not wish for. So in this case, this was a group at DTU in Denmark. They looked at different paper waste fractions, and they found, for example, for one pollutant here, bisphenol A, that concentrations were extremely high in thermal papers. This is to be expected because there it has a function. It has a function of developing the colors better. But what was a bit worrying is they also found it in all other waste paper fractions, and there it should not actually be. And that indicates that maybe this substance was entering all the other waste paper streams through recycling systems. And that is a bit worrisome because you don't want to have these substances in your products. And we need to take care that we keep control of those cycles. Also for other materials like plastics, if you read the news in the last years, you have maybe heard of lead pollution in plastic toys, and it's not really clear where it's coming from, but it's quite likely that that was also a product of recycling, that you just simply recycled some fractions into these toys, which maybe should not have been recycled. So we have to be careful not only to increase always recycling rates, but to look at the quality, really, and to maybe also sometimes take the conclusion that it's better to recycle a bit less for the sake of not only product safety, but product quality in general, and also environmental impact. So let's again have some intermediate conclusions. So what I wanted to show is the quality of the waste materials influences, first of all, the potential use of the recycling products, the quality. It also influences the environmental impacts, is seen, for example, in the steel example, where we have more energy consumption if we have bad secondary material flow quality. And it may introduce hazardous pollutant concentrations. So increasing the quality through various measures, and only some of them are mentioned here, but I'm sure you are more creative than I in this field, that really makes sense and can lead to significant savings in energy, environmental impact, and in the reduction of health risks, which maybe so far we haven't seen so much, but if we increase our recycling rates, that may actually become a problem. It's also clear this is a topic which has not been regarded so far. So far, recycling has always been good, no matter how you do it. And that maybe is something where we have to have a closer look to be a bit critical about this and give a quality, let's say, ranking to different recycling processes. Okay, let's put this again in our waste bin. The last topic that I would like to address is, so far, what I have shown you is some examples for the application of MFAs, material flow analysis, and LCAs in waste management systems. But now the question comes up, can we combine this a bit more smartly? And here is the general idea. So for a certain region, you have different wastes and you have different resources, and you have a certain infrastructure. So for a certain recycling infrastructure and disposal infrastructure. Now, what you would like to do is you would like to distribute the waste materials and the resources, the other resources, which you can substitute, in such a way that you minimize environmental and hopefully also economic costs. So that would mean, if you want to do this, such type of comprehensive analysis, you would start from the material flow analysis of the current system. You would then identify the different pathways that these waste streams could also go as an alternative. You could use the life cycle assessment for the evaluation of the environmental impacts that result. And then you can optimize the system, for example, for environmental impacts and economic impacts. And as a result, you get again a material flow analysis which improves, optimizes your waste flows going to processes which hopefully then do an improved job in comparison to the current situation. And here you can also include new technologies if you have the data, the environmental data, to see a bit what their role in the system would be. Of course, this is all very theoretic. When it then comes to practice, you have to run over this again. But it gives you a bit of a benchmark of where things could go, and it gives you maybe some help in developing strategies for waste management. Such type of analysis initial types of analysis have been done. So this is a group from TU Munich, and they, for example, did such an optimization system for wood flows. I'm not going into the very details, but they started out from a certain supply of wood, which is available. I think in their case it was Bavaria that they looked at in terms of system boundaries. They looked at different ways of how this wood could be used in a simplified manner. Introduced also the possibility of cascading to the extent that it's possible, because for wood you always have a type of downcycling. And they considered then the products that you're producing and gave credit for it for alternative products that you're substituting with these types of applications, so either energetic or material products. And again, looking at the overall environmental impacts, giving the benefits, and looking here at the impacts that you're creating with your new system. And again, they came out then after the optimization with such a type of flow analysis, showing them a bit where the wood flows should go. The percentages show, in comparison to the current use, how much more of these products are produced. And for example, here they concluded that cascading would be good, but they also showed a bit in the overall system what the conditions are, namely, for example, that at the end of the cascade you must have, again, enough material to burn. That was a kind of prerequisite so that the environmental impacts would really be lowered. If you lose the material in the process, for example, because you in the end put it somewhere where it cannot be used thermally again, for example, in some kind of mixtures. There are mixtures like concrete, wood, and so on, then you're not going to recover these fibers ever again at the end, then that the material cascading wouldn't pay off here. This is now in development in various groups, also for larger systems. So I've heard at DTU for biomass flows in general, they are doing at the moment a kind of optimization of the material flow analysis using life cycle assessment. This is another example where the complete waste management system is going to be analyzed in this way, and we will see in the future what comes out of it. Good. With that, I come to the final conclusions, and I will recycle some of the previous ones. So the first point is what we do with waste matters. So depending on what kind of process we choose for our waste treatment or for our recycling system, we do find various environmental impacts. So we do have differences, and it's quite important to look at that. It's also quite important to look first which waste materials really make a difference in the overall system in order to focus our efforts really on those processes which matter. But also, it's not only about the process, but also the quality of the material, secondary material flows, and then, as a consequence of the products that you produce, that is extremely important, and often it is actually the most influential factor. The quality of waste is also important, not only because of the direct environmental impacts, but also because of the quality of the product as such, because sometimes the quality then in the use is not as good, and also because we may have health impacts if we introduce hazardous pollutions. And in the end, the tools, if you hadn't recognized MFA, LCA, these are tools of industrial ecology. I think they can be quite useful in prioritizing efforts, in showing where hotspots of environmental impacts lie, in revealing trade-offs, understanding them at least, and hopefully also to derive then strategies for a better waste management. Okay, with that I want to conclude. Thank you very much for your attention, and also thank you to the funding organizations and the people that helped in elaborating the research that I showed.
Thank you, Stefanie, for this tremendous presentation. We can do whatever we want on valorization, but at the end, this has to be evaluated, and that's why we need such approaches. She was on time, quite on time, perfect, and we have time for questions.
Thank you for the presentation. I'm Marco Castaldi from City College in New York. I have two primary questions, and one is something that you just touched upon in terms of the quality of the material. So in these analyses, do you include, or does it include, the feedstock that comes in being mixed? So for example, paper. You do not get only the high quality paper, you also get recycled paper. And this then cannot be recycled again through that process. So that's one question. Yeah. Does it include the mixed?
Shall I answer this one before you? You're absolutely right. This is exactly what matters. And in many of the analysis, this is not considered. This is the point I wanted to make. But very often, it's quite important actually to do so, because it does make a difference what you substitute. Also in terms of the environmental impact, because if you look at the whole production chain of the primary product, it makes a difference what kind of quality you then avoid. So you're absolutely right, this is important, and in many of the analysis that you find, this is unfortunately very simplified, done in a very simplified manner. So you need to look when you have such studies whether it has been done or not. We try to do so, but
okay, yeah. So in these you try to include this.
Yes.
Okay, and then I guess my other one relates to sort of the output on side. You had done the analysis of, say, the municipal solid waste incinerator, and you looked at electricity and heat, electricity maximum and heat maximum. But in terms of the types of energy, the joules, is it the same quality of heat? Because this makes a very big difference. One, you could extract work, and the other one you cannot.
Yeah. This is also something which traditionally I think has been looked at quite a lot. Yeah, you can do so in the substituted heat again, right? So here you try to find substitution products where you have the same level. Exactly. So if it is low temperature heat, you cannot use the same system for your avoided burden.
Sabu Thomas, Mahatma Gandhi University, India. It's a very nice talk. And I have a small question. Did you look at some of the health-related issues of incinerators, on a global basis?
Sorry?
The incinerators, some of the health-related issues of incinerators when you use plastics and etc. for burning. Incineration, the health-related issues.
So we have looked quite closely at incineration and the various environmental impacts, also at different technology options, but I haven't shown this here to simplify a bit. Do you have any particular interest in?
Yeah, some health-related issues. Some of the other big factors.
As definitely, for example, if you compare, for example, incinerators with a proper flue gas cleaning system and without, there is a huge difference. All of this was conforming with European law, and we had quite sophisticated flue gas cleaning systems attached. But actually, there is a process model behind this, and there you can also switch off the flue gas cleaning system, and then you see that you will increase the impact, not for climate change, of course, but then you have to look at other impact categories. I didn't want to make it too complicated, but for example, for human toxicity and ecotoxicity, where then you would have an increase, a definite increase.
You have made a calculation of climate change impact based mainly on CO2. Isn't the drawback, since as you have seen, most of the streams that we are dealing with are contaminated, I mean, whatever pollutants, metal, inorganic, and then it comes with the gas base, which are mainly composed with pollutants, with a certain, maybe in terms of concentration, they are low, but in terms of impact, it could be even higher than the CO2 itself. Is there any way to discriminate between this climate change based on CO2 calculation, the real impact? Toxicity, I would say, or as a safety concern.
Yes. It was not only CO2, but all greenhouse gases, but you are right. I mean, this is not the only issue. So especially for toxicity, that the metals and so on, this is important to consider. Toxicity, we can do, but we need to take into consideration that all the methods which exist at the moment are still attached to extremely large uncertainties. If you want to make these comparative assessments, the problem there is that each of these, what we call as impact factors, has quite a large uncertainty range. But this is not to say that we should forget about this. Definitely the study has also been done and included for most of the case studies that I showed here, also in terms of toxic releases. Absolutely.
Jannie van der Venter from Melbourne, Australia. I'm usually asking questions about concrete, but this is totally different. I'm very interested in your perspective on bisphenol A, which is often underrated as a carcinogenic agent, and I think there's a lot of silence in medical research about that effect. But I'm actually shocked about the distribution that you can get, not surprised now, in plastics. To what extent do you think that message is kept silent in industry, because it has a huge impact in terms of the utilization of plastic, but also how paper products, which often have plastic coatings, are handled by all of us all the time. For example, the receipts we get, thermal receipts printed every time you use a credit card, etc., etc. Is this message being kept silent, or do you think we should shout louder about it?
I don't really know, and I'm not the expert in BPA. This was actually a study that was conducted in Denmark, and I found it quite striking what they found, especially what you are saying, that there are some waste paper fractions which have extremely high concentrations, which seem to then pollute all the others. But I'm probably the wrong person to ask this. I think then we would have to go back to the original researchers and ask them about that. Whether that is intentional or not, I don't know. But it's clear that these matters, I think they have not been investigated too much. Yeah. Especially how these pollutants then, this was just analyzing some waste streams, but how they behave during the whole cycle, where they are added, what exactly leads to that cross-contamination. To understand this, it hasn't been done yet.
Thank you, Stefanie. Again, there's one more.
One more? Thank you. My name is Bernardo. I'm from the University of Minho, Portugal. Thank you very much for your most profound and energetic presentation. The last presenter told us that life cycle thinking papers coming to WasteEng have been diminishing in simple terms. But this is a very close focus, of course. If you look at full picture, can you please tell us how are the literature on life cycle thinking, considering all tools, occurring in the last few years? Is it increasing, stabilizing, or decreasing?
Sorry, can you repeat the somehow acoustically?
What is the trend of literature on life cycle thinking in the last few years?
I have not really looked at the papers and don't have any statistics here. I think in general it is increasing. Whether it's also increasing in waste management, I think so, because especially you have some movements which call for these type of analysis, like for example the circular economy in Europe, but also in many other parts of the world. I think a lot of these tools are increasingly used now. But I haven't got the figures, sorry.
Thank you.
Thank you. Yeah. Let's thank the So we're going to move forward now. It's a session, now we're going to have a coffee break, which is going to last until 11:30, delay in 5 minutes, together with the poster session. We're going to make this in parallel. And you could, by getting out this building, identify the session postal sectors, as I said, but there is a coffee break here in this main room outside and also in the front of postal session. Please be on time at 11:30 for the parallel session. Thank you.